Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over how to find limits graphically and numerically. All right, the instructions for the problems that we're going to be solving today are as follows. You're to estimate the limits by completing the table provided, and then we're to confirm our answers by graphing it in the graphing calculator. Okay, so problem number one, we have the following limit right here. We are to find what the limit is numerically first and then graphically afterwards. All right, so if you take a look at this expression, what we're looking for is the limit as x approaches 2 of this entire function right here, this rational function. So what the question is asking is, as x gets arbitrarily close to 2 from the left and the right, what does this function approach? Okay, all right. So let's take a look at this table for a second. One thing you'll notice is that we're getting close to a certain number. Between 1.999 and 2.001, that's 2. Okay, 2 is right here. So we're going to be approaching 2 from the left, all right? And then we're going to be approaching 2 from the right. If these two values are approaching the same value, then that will be the result of the limit as x approaches 2 from both sides. All right, remember, if you do not have any sign next to x, next to what x is approaching, it's a double-sided limit. You're looking at both left and right-hand limits. Okay, so if the results we get are different, let's say these two pattern of numbers are approaching extremely different values, then the limits will not exist. Okay, all right, so let's go ahead and get started. What we're going to do is we're going to use our graphing calculators to compute the output of inputting these input values into the function. Since I want to save time, what I'll do is I'm going to store this function into my calculator and then evaluate it for different values of x. So let's do the following. We have negative parenthesis x minus 2 divided by parenthesis x squared minus 3x plus 2. So I'm going to store that in, let's store it in f of x, okay? In f of x. Enter. All right, so just to test to make sure that I have the correct function stored in f of x, I'm going to call back the function f of x, enter. Well, what happened is that the calculator reduced it, okay? It reduced it into negative 1 over x minus 1. So that's the reduced form of this function here if I factor out the denominator, okay? All right, now let's go ahead and start inputting values. We're going to do 1.9. So if I want to enter 1.9, I'll simply delete x and type in 1.9, enter. I needed numerical value, so diamond enter will give me the decimal expansion of negative 10 over 9. So we have negative 1.111. So let's do it to 4 decimal places. All right, so this one is negative 1.1111. All right, so for the next one, I'm just gonna add another 9 here just to save time. Press diamond enter to get the approximate result. Negative 1.0101. So it's negative 1.0101. All right, next we're going to add another 9 there. We have, oh snap, diamond enter to get the approximate result, negative 1.001. So negative 1.001. Now, if you take a look at these numbers, what does it look like it's approaching? It looks like it is approaching negative 1, right? So let's go ahead and write that down. The limit as x approaches 2 from the left of x minus 2 negative x squared minus 3x plus 2. The left-hand limit is, it looks like it's going to be negative 1. All right. Now let's take a look at what the right-hand limit is. So I'm just going to start from 2.1. You take out the input, replace it with 2.1. You have, let's do down and enter, negative 9091 to 4 decimal places. So negative 0.9091. All right, let's get closer. We're getting closer to 2 from the right-hand side, okay? So 2.01, you're gonna get 0.9901. So negative 0.9901. All right, and then the last one, f of 2.001. We have negative 9990. Okay, so we have negative 0.9990. So what do you see if you examine these numbers? You notice that you're having more and more nines as you get closer and closer to 2. And if you have infinite number of nines, you just round it up. This is going to be, I'm sorry, getting closer and closer to negative 1. So if you have infinite number of nines, round it up, you're just going to end up with negative 1. Okay, so the right-hand limit as x approaches 2 from the right of the function x squared minus 3x plus 2 is equal to negative 1. Now, since both limits are the same, guess what? The double-sided, this implies that the double-sided limit the limit as x approaches 2 of the function, negative x minus 2 over x squared minus 3x plus 2 is equal to negative 1. So this is just our numerical result. Okay, so now we have to verify our answer using our graphing calculator. What this is basically saying is that as you get really, really close to the x value of negative 1, the x value of 2, the y value you'll be approaching should be negative 1. Okay, so that's what we should see when we graph the function. All right, so let's enter it into our graphing window. I'm just going to graph the function f of x. Is already stored in a calculator, so just graph that. I'm going to zoom standard in a second. Okay, so we're getting really, really close to positive 2. So what is the y coordinate as you get really, really close to positive 2? Let me create a zoom box, okay, so we can focus in on the relevant part of the graph. So let's just make it a little bit smaller. Enter. Let's go to the right past positive 2. Bring it down. So I want to see what x value the function is approaching, what y value the function is approaching as x gets really close to 2. Okay, so you see this is intended x value here. Just trace, get really close to 2, so f3. At 2, let's enter 2, enter. There isn't any y value. That's because you have a removable discontinuity there. But when you scroll to the right of 2, you see what number we have here? Negative 9.5. It's close to negative 1. And if you go to the left of 2, you're close to negative 1. So graphically, we can easily conclude that when it gets infinitely close to 2 from both sides, the y value you're going to be approaching is negative 1. So we have a graphical confirmation here. All right, let's take a look at question number 2. So for question 2, we have another function here. We are approaching 0 this time. So what's going to happen is that we're going to be approaching 0 from the left. So this is the x value we're approaching, okay? We're going to be approaching 0 from the left-hand limit. And then we're going to be approaching 0 from the right, okay? The right-hand limit. And then we'll see if we get the same value, and that will be the value of the limit. If we're approaching different values from the left and right, then the limits will not exist, okay? So we're going to do this numerically first, and then we will confirm our answer using the graphing utility. So we are now storing a new function in our calculator. So we have the square root of x plus 4, close that, minus the square root of 4, close that, close your numerator divided by a denominator, which is just x. So we're going to store this in f of x. It's going to overwrite what we stored in it before from problem 1. Enter. Done. Let's call up f of x just to make sure that our entry is correct. So let's see, f of x, enter. All right, so I will actually simplify that for us. All right, so now we're gonna start plugging in the values and see what outputs we get, okay? So I'm just gonna do these 3 and then write it into my table. So negative 0.1, enter. So we have 0.2516. So it's 0.2516. So 4 decimal places. All right, we're getting closer to 0, okay, from the left side, tossing a 0 there. And then that gives us 0.2502. 0.2502. So see what's happening with the numbers here? All right, let's do one more, and then we can make an informed guess as to what the function is approaching as x gets arbitrarily close to 0 from the left. Okay, so let's do that and enter. 0.25002. 0.2500201. Well, let me see. 002 is just 0.00 like that. All right. So can you see what this number is approaching? Is getting really, really close to 0.25, okay, which is 1/4. That's from the left, okay? Now let's go ahead and approach it from the right. But before we do that, left-hand limit. The limit as x approaches 0 from the left of this function, root x plus 4 minus root 4 over x, the left-hand limit is 1/4, okay, based on our numerical investigation. Now, what's the right-hand limit? As we get arbitrarily close to 0 from the left, from the right, what does this function approach? Okay, so we're going to enter these values into our calculator and then examine the pattern and see if we can determine what it's approaching. Okay, all right, so let me go up here, call this one, start from 0.1. All right, I'll just delete the minus. So for that one, we have 0.2485. 0.2485. So 0.2485. Okay, now let's get closer. Let's get closer to 0 from the right. Tossing a 0 there. And then we have 0.2498. 0.2498. Do you see what's happening? Well, let's enter the last one, f of 0.001, and then we get 0.249. Ooh, if we round it up to the 4th decimal place, it's 0.2500. 0.2500. So you see, the right-hand limit is 1/4 also. So what's our conclusion? Based on these two, we can conclude that the double-sided limit as x approaches 0 of the function root x plus 4 minus rad 4 over x, we can conclude that it is equal to 1/4, 0.25, okay? And then let's check it in our calculator, see if our answer agrees with the graphical situation. We already have f there, so let's graph it again. Now what we're doing is we're going to be getting really, really close to 0 from the left and right, okay? So this is a nice graph here, so let's trace f3. If it hits 0, It doesn't really give us anything. So let's go to the left. 0.2503. Excellent. From the left is approaching 0.25. Go to the right. 0.249 is approaching 0.25 also. Okay, so we have a graphical confirmation that our answer is in fact correct. All right, let's take a look at problem numbers 3 to 6. In these problems, we're going to be using the graphs to determine the value of the limit, okay? All right, so instructions use the graphs to estimate the limit, justify non-existence of limits. So if a limit does not exist, we will have to state why. All right, so for problem number 3, we have a piecewise defined function, and we are approaching 1. This is 1 right here. Now, this is a rule we're going to be using. Look at this table to the right. Now, we have finite and infinite limits. In this problem, we're going to be dealing mainly with finite limits. Basically, you're going to be approaching finite numbers in the direction of the x. So whenever you're working with finite limits, you're either going to be approaching a point, a vertical asymptote, or you're going to be oscillating, okay? If you're approaching a point, it could either be a closed or an open point. It doesn't matter. It's exactly the same thing, okay? If you're approaching a closed or open point, the y-coordinate will be the limit in that direction. If you are approaching a vertical asymptote, if you're heading upwards towards the upwards direction as you approach that asymptote, then your limit will be infinity. If you're heading downwards, then it will be negative infinity. If you're oscillating as you approach that specific x value, then the limit does not exist since it doesn't approach a specific x value. In the case of infinite limits, we'll be dealing with that later. You're either going to be approaching a horizontal asymptote, increasing end behavior, or a decreasing end behavior, and these are the possible answers that you're going to have. Okay, so let's take a look at problem 3. Remember, if you do not have a direction, is a double-sided limit. In order for the limit to exist, the right-hand limit and the left-hand limit must be the same. Okay, so let's start with our left-hand limit. So what is the limit as x approaches 1 from the left of the function? All right, so what we're doing is approaching 1, this particular value. So as you're approaching 1, what do you notice? Are we approaching, is it oscillating towards 1 from the left? So this is 1 from the left, just in case you don't know. 1 from the left, you go in this direction. Is it oscillating? Is it a point, open or close, or is it a vertical asymptote? We are approaching a point that's open, okay? So the value of the limit is going to be what? Since you're approaching a point, an open circle, the y-coordinate of that open circle is your limit. Okay, so in this case, the y-coordinate here looks like it's about 2.5 right here. The y-coordinate is 2.5. So the left-hand limit is 2.5 or of f of x or 5/2. Now, what is the right-hand limit? Even if the left-hand limit is approaching an open circle, it doesn't automatically mean that the right-hand limit will exhibit the same behavior, all right? We have to investigate both. So the right-hand limit, now you're approaching 1 from the right side. What are we approaching? We're approaching the same open circle, okay? So we are approaching a point that's not there at that particular area of the function. So the y-coordinate of that point is going to be our right-hand limit, which is the same thing as the left, 5/2. All right. So conclusion: the limit as x approaches 1 from the left and right, which is written as just 1, is equal to 5/2. That's our answer for question number 3. All right, let's take a look at question number 4. This is another finite limit example. We're going to be using our rule to the right. Again, in this case, we are approaching -3, okay? It's a double-sided limit. Since there's no sign indicated there, we have to examine the left and right-hand limits. Make sure that they're the same before we can conclude the existence of the double-sided limit, which is going to be equal to the right and left-hand limits. Okay, so let us approach 3 from the left-hand limit. So the limit as x approaches -3. Okay, that's what we're approaching. As we're approaching -3 from the left of the function, we're approaching what? We're approaching an asymptote, an oscillating behavior, or a point that's open or closed. We are approaching an open circle, a point that's not there. So the y-coordinate of the point of that open circle is our left-hand limit. The y-coordinate is -2. Down. All right. Now let's go from the other direction. What is your right-hand limit? Your right-hand limit, you're approaching the same point. Okay, the same open circle, -3. The point is not defined at that particular piece of the function. So the right-hand limit, the limit as x approaches -3 from the right of the function, is the y-coordinate of that point that you're approaching, which is also -2. So what is our conclusion? Our conclusion is that the double-sided limit, written as limit as x approaches -3, of the function is equal to -2. So that's the answer for question number 4. All right, let's take a look at question number 5. We are still dealing with a piecewise defined function. Okay, so in this one, we are approaching 2 from both sides. So double-sided limit, since there's no sign provided here, no direction. Okay, so let's start off by approaching 2 from the left. Okay, approaching 2 from the left. That is your left-hand limit. So your left-hand limit is the limit as x approaches 2 from the left of the function. In this case, you can clearly see that we're approaching a closed point. All right. So since we're approaching a point, the y-coordinate will be the limit. So it looks like we're approaching 3.5 or 7/2. All right. So 7/2 is our left-hand limit. Now, what's our right-hand limit? To the right of 2, we have a different function. We have this quadratic function here. So the limit as x approaches 2 from the right, so we're now approaching 2 in this direction. What are we approaching? We're approaching an open circle, right? Or a point that's not defined at that particular location. The y-coordinate is the limit, so the y-coordinate is 0. So for this one, the y-coordinate is 0. That's the limiting value. That's the output that this function is approaching as x gets arbitrarily close to +2 from the right direction. What do you notice here? These two limits are different. So what do we say? The limit as x approaches 2 from both sides of the function does not exist. What's your justification? Because the left-hand limit and the right-hand limits are different. Okay, because the limit as x approaches 2 from the left of f of x is not equal to the limit as x approaches 2 from the right of the function. Okay, so that's sufficient justification for the non-existence of the limit. The double-sided limit at x equals +2. All right, let's take a look at question number 6. We're approaching 3. This is a double-sided limit. So let's go ahead and mark it. Bam, right there. Okay, so what do we have for our left and our right hand limits? So let's start approaching 3 from the left side. The left hand limit. The limit as x approaches 3 from the left of this this function we have here is going to be what? Well, we're looking at, what are we approaching? We're approaching a circle, a point that's open, an open circle. So the y-coordinate of that open circle is the limit. Trace it there, -1. Now, There goes your left-hand limit. Your right-hand limit. Now we're going from the right direction, approaching 3. So that's approaching 3 from the right. So this is positive 3 right here. So what are we approaching as we are approaching from the right? We're approaching an open circle again, a point that's open or it's not defined at that particular location. The y-coordinate is the value of your limit. Okay, so what's the y-coordinate there? Limit as x approaches 3 from the right of f of x. Just trace the y-coordinate of this open circle. Okay, positive 1. The right-hand limit is positive 1. So what is our conclusion? The limit as x approaches 3 from both sides of the function does not exist. Why? Because the left-hand limit as x approaches 3 from the left of the function, does not equal the right-hand limit, the limit as x approaches 3 from the right of the function. All right, because of this inequality, we have the non-existence of this limit at x equals, as x approaches 3 from both sides. All right, let's take a look at problem number 7, the last one in this installment, part A of finding limits numerically and graphically. Now we're approaching negative 3 from both sides. Okay, so let's mark it negative 3. Bam. Let's start by approaching 3 from the left. Okay, so we're approaching 3 from the left-hand limit, actually negative 3 from the left. All right, so this is the left-hand limit. All right, so what is the limit as x approaches negative 3 from the left? Okay, so if you look at this scenario, as you're approaching negative 3 from the left, are you approaching a point, a vertical asymptote, or are you oscillating? In this case, you are clearly approaching a vertical asymptote. So now this is the case we're going to be looking at. Whenever you're approaching a vertical asymptote for a particular x value, you want to ask yourself, what's the behavior of that function from that direction? Are we going up or down? From the left, the function is tending upwards towards where? Infinity. So guess what? The left-hand limit is equal to positive infinity. Now, how about we switch directions? What if we go from the right-hand side? What is the right-hand limit? So we're approaching, this is negative 3 right here. We are approaching negative 3 from the right. Bam. What is the right-hand limit? What is the limit as x approaches negative 3 from the right? From this direction, we are also approaching the same vertical asymptote, but we are tending towards negative infinity. We're heading downwards. Okay, so remember, if you have vertical asymptote, you ask yourself, am I going up or down? If you're going down, negative infinity, up infinity. So this one is going to be equal to negative infinity. So what's our conclusion with these two results? Conclusion is as follows. The limit as x approaches negative 3 from both sides, since no sides are indicated of the function, does not exist. Justification, because the left-hand limit as x approaches negative 3 from the left of the function, is not equal to the right-hand limit, the limit as x approaches negative 3 from the right of the function. Okay, so that's the answer and the justification for the non-existence of the limit as x approaches negative 3. Thank you so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your study of limits, do give us a thumbs up. Your positive feedback is very important to us. If you have any questions or comments on this presentation, just place that in the comment section below and we'll be more than glad to support you. Don't forget to subscribe to our channel for updates to other cool AP Calculus tips such as this. More things can be found on math.serve.com. Thanks again for watching and have a wonderful day.